So hello, everyone. Welcome to another talk of the Recod.ai, the Artificial Intelligence Lab here at the Institute of Computing, University of Campinas, Brazil. Today, we have the pleasure to count with Dr. Hugo Carneiro. He's going to talk to us about neural learning for interactive robots. Hugo is a postdoctoral research associate of the Knowledge Technology Group at the University of Hamburg in Germany, working in research topics that include cross-modal learning, social attention, emotional recognition, and active speaker detection. He received his Doctor of Science degree in Systems Engineering and Computer Science from COPPE, Federal University of Rio de Janeiro, in 2017. His research interests include artificial neural networks, computational intelligence, cross-modal learning, computer vision, NLP, natural language representation, interpretability, and learning theory. Hugo, thank you very much for accepting the invitation. Leopoldo, thank you for connecting us with Hugo. Hugo, the stage is all yours. I will stop sharing my screen. You can go ahead and share yours. Normally, we have about 50 minutes for talk and then 20 minutes for questions, okay?
Okay, thank you. Can you see my screen?
It's coming.
Okay.
Yes, it's ready.
Okay, so thank you, Professor Rocha, for your introduction. Good afternoon, everyone. I am Hugo Carneiro. I work as a postdoctoral research associate at the Knowledge Technology of the University of Hamburg, and I present my talk on learning for interactive robots on behalf of Professor Stefan Wermter and our team, the Knowledge Technology team. Neural networks are part of our everyday lives. Examples include generative model networks like photorealistic morphing in the case of aging a person, in this case, Ryan Gosling. Text completion, autocorrection, as well as personal assistants like Siri, etc., which helps us with queries. For instance, how is the weather this evening? There are also cases like Alexa that are similar to Siri as the personal assistant, but they are usually embedded in our smartphones and connected to other devices, as well as self-driving cars that have a number of assistant capabilities. However, complex cognitive functions are not only simulated in cars, but also in robots, and as well as some games such as Go, which are so complex that they can currently only be solved by using the same mechanisms that are used in self-driving cars. And in more complex systems, just like Alexa, usually they are a collection of different systems with an engineered pipeline of intelligent modules, for instance, speech localization, speech recognition, natural language understanding, with each one of those modules with a different purpose. In this video, for visual perception, this shows a convolutional neural network performing image segmentation for a car camera. The colored regions represent objects or regions that are detected by the network, and this gives the car some form of environmental perception and forms the basis for more action-oriented algorithms that can plan ahead and act based on their environments. But it's important to realize that our world is cross-modal with inputs from various sensory modalities such as vision, speech, haptics, and so on. How one can build intelligent robots to interact in such a cross-modal world? The building of such robots may be of help, for instance, in improving domestic human-robot interaction, especially in elderly care and healthcare, and focusing on adaptive systems that learn from and with the users that should provide natural human-like interactions. For the cross-modal learning, it's important to realize that in the brain, different social cues are processed in distinct parts of the brain. For instance, the auditory cues are processed in the inferior colliculus, while the visual cues are processed in the retina and in the cortex. And the superior colliculus is the midbrain structure responsible for integrating the information from those different modalities. In 2014, our group developed supercalculus model, actually a novel self-organized model that learns the topography of noisy inputs from auditory and visual input. And from them, it can compute the PDFs for the probability density functions for the location of both stimuli. With the supercalculus model, our group also managed to program an iCub robot to direct its gaze towards the origin of audiovisual stimuli that were presented to it, as can be shown in this video. This year, we use sequential cross-modal integration as a way to detect salient regions in real-world videos. And by generating different feature maps from several social cues, such as audiovisual information or gaze information, or even emotional recognition, and emphasizing some social cues through a direct attention module, such that all of them would have the reasonable contribution to the salience prediction, we could provide the most salience region in a given footage. The salience prediction model that was then applied in a cross-modal social attention conflict resolution problem. In this task, trial with 3 human avatars were created, where the central avatar would point its gaze towards one of the peripheral avatars. And one of those peripheral avatars would provide an auditory cue that, in the case here, hello, that peripheral avatar provide that auditory cue would not necessarily be the one the central avatar looked at, what we call here in this case, an incongruency in the social cues. And we opted for using facial masks on the avatars to provide that congruency, thus the cross-modal social attention conflict. And a mouth, without the face mask, the mouth movement itself would probably end with any possibility of incongruency, because the visual and auditory cues would become congruent, because there will be a mouth movement and the sound from that avatar with the mouth movement. And besides that, the use of face mask was also a way for us to show the importance of eye-gaze communication these days, because everybody is using face masks due to the COVID and so. In this case, for our experiments, we asked human participants in China to determine the origin of the sound that was coming from the left or the right, independent of the eye-gaze direction provided by the central avatar, and to respond by pressing a key on the keyboard. Similarly, the iCub robot was subject to those trials where it would turn towards the region where the sound might be coming from, based on the salience prediction model. And the results we got also indicate that the robot has a very human-like behavior, performing better when the visual and auditory cues are congruent rather than when they are incongruent. I'll show the footage of how it works with this trial. Please pay attention to the eyeballs of the iCub that change based on the examples provided.
Hello.
Right here, for instance.
Hello.
Another important characteristic in determining salient regions is speaking activity. Roughly 70% of the time, people tend to focus their attention to the mouth of other people. And when those people are talking, this value tends to grow up to 90%. This year, I used the concept of face-voice association to detect the speaking activity. The state-of-the-art models usually focus their attention on inter-speaker relations for that, but context alone is not able to handle cases more complex or more ambiguous, such as when there are simultaneous people, two or more people speaking at the same time, or when the speaker is not visible or not in the scene. Our model was based upon the active speakers in context, which uses the context for that. It actually gets information from from some speakers in the scene, usually up to 3, encode their audio information, and through a self-attention module, it can provide a context refinement. And our addition was a face-voice association model, which could try to extract facial information from the auditory input, thus the cross-modal part, and thus being capable of determining specific characteristics of the speaker, for instance, their age, their gender, so on, and being thus capable of disambiguating those ambiguous scenarios. In this case, for instance, these 2 women who start talking at the same time in the beginning of the scene, but the active speakers in context here, as ASC, is not capable of determining that, because as soon as the context realized that the most prominent, the most salient woman here at the front, that she's talking, it automatically determines that this woman should not be talking because there is already someone talking in the context. However, our model called Favor for face-voice association, it does not suffer from this problem, avoiding this problem of be capable of marking only one person, so it can actually mark those 2 women at the same time. So here I present the ground truth, what is to be expected, what the art model does, and what our model does in this scene. Those 3 scenes will be presented at the same time for you, for the sake of comparison. In this other scene, the speaker is not actually in the scene. The speaker is a woman who's not visible in the scene. Actually, she's talking from another part of the scene, and the picture or the scene is only focused on this guy who's silent throughout the whole scene. The guy should be always marked as not speaking, as you will be able to see here in the ground truth. But the active speakers in context, the state-of-the-art model, actually marks him as actively speaking when he uses a towel to cover his face, and when, because of the sound in the background, and then after using the towel, the system thinks that he's talking. And although our model also marks him as audibly speaking, as soon as it realized that the voice is not from this man, but from a woman, it prevents that from being kept as speaking and marks him automatically as not speaking. Although this active speaker detection model is not still implemented in our robots, active speaker detection may be of aid in more complex real-world scenarios with simultaneous speakers, background noise, or even with someone speaking from behind the camera. So it's our intention to use that in the near future. Well, our group also integrated posture and motion in models, and through the integration of posture and motion to our cross-modal robots, they can detect events such as domestic accidents, such as a dangerous fall, or when, for example, a faint or something like that. And also the use of HRI may also reduce some case of false alarms. If in the case of the person falling, actually, the person can get up again very quickly. And here we also had a data set. For that, we had a data set of 10 full body actions using 3 centroid representations from a 3D skeleton model with actions that include walking, jogging, sitting, picking up, falling down, standing up. And the 3D body representation from that information can be very useful in this case, in real-world human-robot interaction scenarios. For instance, because there can be cases in which there are bad light conditions and so on. So in this case, that depth camera can be of use. Pose motion features usually are processed with a hierarchical, and in this case, are processed with a hierarchical self-organized architecture to learn prototype action representations in an unsupervised fashion. Action label mappings here are learned in the last layer here called GSTS from superior. And this is done via an associative mechanism to attach symbolic labels to those GSTS neurons. Since the learning process is carried out using a growing self-organized architecture, new actions can be added without retraining the system on the whole data set, which is one of the benefits of using growing self-organizing model, just in this case, a growing when requiring neural network. Here we have a hierarchical self-organizing architecture that same hierarchical self-organized architecture was trained on a set of 10 gestures in a human-robot interaction scenario. The architecture here receives as an input 3D features from hand motions, which are extracted in real time from depth information, with gestures just like showing that just go right, go left, zoom, and so on. Those kind of feedback from learning human motion, they are important in rehabilitation, because in those cases, the person is required to perform a set of well-defined movements, and the self-organized architecture trained on a set of training movements using those 3D body information is able to detect incorrect body posture and motion in terms of some body motion patterns that do not match with those of the training sequences. And recursive neurons may be of help in that self-organized network as a way to capture the spatial temporal properties of the input. This mechanism, it can provide some visual feedback to the user in a series of training routines. In that case, for instance, the person doing some exercise with the arms, or for instance, weightlifting. In this video, it's marked in red where the person is doing the wrong, the movement in the wrong way, which can possibly harm him, her, or bring some kind of damage. We also integrated pose, motion, and also language with action word mappings that were learned in an unsupervised fashion on the basis of the co-occurrence of audiovisual dynamic patterns from the body motion and the speech of the person, and connect patterns between those and connectivity patterns between the last layer of the visual processing and the symbolic layer are then learned during that learning process. And in this way, it is possible to predict the label of a novel visual pattern in the various sequences, right? And retrieve the prototype visual representation of the symbolic label in this case, for instance, standing, sitting, walking, jumping, jogging, crawling, and so on. And this architecture is also able to learn robust action word mappings, also when all the labels are provided in the case of a semi-supervised learning. The previous example processed 3D body features from depth information, but while depth is a series of advantages, they also have some limitations, and it may be of interest to process raw visual information. In the spirit of deep convolutional learning, our group extended the self-organized architecture to extract significant features from the raw visual input using deep neural network self-organization. And the hierarchical architecture processes visual input with increasing spatial temporal receptive fields. The learning of those visual features is completely unsupervised in that case with autoencoders. And an associative learning mechanism is used to learn mappings between prototype visual representations and symbolic labels. For the recognition of some transitive actions, that is, actions related to some kind of object, one should get information about the objects that are being manipulated. Visual cues of body pose and the objects are processed with the self-organized networks for learning prototype actions and for learning the prototype actions as well as the objects and for associating them in an unsupervised fashion. This architecture is suitable for online action recognition, that is, when the label is output after each data frame. The classification of the model has been evaluated on the Cornell activity dataset, benchmark dataset of daily activities, and the evaluation and leave one out clause validation indicated its classification performance is similar to the state of the art for this dataset. However, our method is advantageous not only in being strictly, however, the method of our group is advantageous in not being strictly supervised as our other state-of-the-art approaches. Additionally, a data set of simulated daily activities has been collected in our laboratory with actions including picking up, placing object, drinking, pouring, eating, talking on the phone, and no when there is no activity. And with the objects of a phone, of a mug, a can, and also a biscuit box. Our group also worked with emotion processing, and one important cross-modal of motion processing is that it happens in different, very different areas of the brain, with areas responsible for perception, attention, and memory, which are connected to make decisions, actions, and for the intrinsic mood of the person itself. And this self-organizing model represents does this the self-organizing model presented here in the slide. It does this cross-modal emotion processing by using the perception, attention, and affective memory mechanisms. It makes use of 4 channels, 2 visual ones, one for the face and one for the movement, for the body movement, and 2 auditory ones, one for the audio channel, one for the speech. And the model is capable of learning joint representations for each modality through the use of cross-channel, one visual cross-channel and one auditory cross-channel. Here we have a video demonstrating how our cross-channel network works based on information from the 2 visual and the 2 auditory channels. In this problem, they use express the emotions as positive, negative, and neutral, and they use the information from the person torso, the face for that. This was a Brazilian from Recife, Pablo Barros, and he's showing that by changing his emotion from positive to negative, that the model here is capable of detecting these changes in the space of just 4 frames, and that the model is also reliable when being subject to different people, because that can have very different forms of expressing their emotions. Here we have Nico. Nico is a robot that was implemented in our group, by our group, showing that it's mirrored the emotional expression of a human participant. And it's important because this kind of behavior is important in enhancing the empathy of humans towards robots, and thus also leading to better human-robot collaboration. Also, for our research on emotional cognition, we have a specialized laboratory with a projection area and with some sources so that we can use the laboratory for experiments with human and robotic participants. In this case, we can work with behavioral data from human participants that can be used to train neural models, thus making them more controllable and reproducible. We can project in our human-robot interaction screen, for instance, multi-person meeting room scenarios of different degrees of realism, ranging from abstract avatars to computer-generated individuals to actual video recordings. As previously mentioned, our research group developed Nico for the use of non-researchers, and Nico brings together some desirable properties that we need, such as physical interaction, active sensing, with social interaction. This is one data set that was created by our group. Its name is EMIL, which stands for Embodied Multimodal Interaction in Language Learning. It contains images of Nico performing infant or child-like object explorations, like scooting a car across a table, picking up a push fruit, shoving a ball, etc. Our group in this for this data set, they recorded the vision, in that case with the left and right camera from the robot's eyes, also the audio and the proprioception, in that case the position of the joints as well as the motor load. And some objects might also look alike, but they have very different weights and sounds. For instance, in the case we have a plastic apple and a real apple, and they have different weights and sounds, and so this can be perceived by the robot, by its proprioception mechanism, and also from the auditory modality. And this data set further contains, and this is an example of him picking up an object and then performing a movement. You can see that the auditory targets here provides some stimuli. There's also stimuli here in the sensory motor perception. And this set also further contains information from external camera recordings as well as the depth recording, and also the natural language description of the action being performed. It's important to realize that there is a benefit when we combine virtual and real environments in the research. This way, the approach for learning from environmental interaction is first developing a secure virtual environment, for instance, simulation programs such as COPPE. And once initial results show that the approach, for instance, a neural network architecture, it works without producing some harmful motor commands, such as harming some joint of the robot or something like this, then we know that we can deploy that approach on a real robot. Here, there's another example of our research combining visuomotor learning and social interaction. In this case, we have non-expert participants teaching Nico how to grasp objects. And in this example, instructions are given to the participants either by a human instructor or the robot via an embodied dialogue system. And when the robot gives instructions such as, please hand me the red tomato, or, oh, I lost the tomato, please give it back to me, users usually are more engaging in their providing their instruction to the robot. As can be seen in the images, participants usually they tend to reach into the robot's workspace and correct its grasping on their own initiative in those cases. And for the task of grasping, our group also developed some different approaches that range from a simple neural module to grasp a single object, to a two-stage approach, where one network, a faster region-based convolution network, locates an object, and an end-to-end neural network performs the grasping, to one-stage approach with an end-to-end learning model capable of object localization and of the object localization and the grasping. Here is the Here is the modular approach. Here's the modular approach. This is the module capable of realizing grasping of single objects in non-cluttered scenes. In this case, there is a video of Nico performing a die. Here we have a two-stage approach. In this case, a faster region-based convolution neural network locates objects and defines their bounding boxes. And through an attention mechanism that masks inputs, a visual motor network can then control its grasp. In this case, people ask the robot to get yellow objects. It says that it is ambiguous, then ask for getting the yellow banana. It then sets the attention to the banana to then finally execute the grasp. And finally, in 2019, our group developed a one-stage network that realized object detection and grasping using a single neural network by fusing the retina net architecture with the grasping architecture previously shown. And the architecture then can learn to detect objects and to grasp them at the same time. However, it's important to note that such complex architectures that learn different tasks in parallel are difficult to analyze and to debug. Therefore, we began to use some visualization methods. Here, the robot is tasked to grasp the carrots. The second image shows which parts of the image the robot identifies as being the carrots. And in the case of the robot, would instead reach for the aubergine for the eggplant. We would know if this was due to some kind of confusion it had when defining what are the carrots, what's the aubergine. Or if this is due to some issues with the motor learning. Here we have an example of a scenario where several of our research streams come together, for instance, language understanding, audio-visual processing, grasping, and so on.
Take the red cube that is in the bottom left corner and put it on the green cube.
Also, here we have some other examples of the visual motor coordination done with Nico, such as rolling a die, as have already been shown. Or grasping and throwing a plush object. And there's also the case of causal problem solving.
I need to pick up the red tomato, but I mustn't touch the rocket with my fingers.
So in this case, it must get the tomato, but it cannot touch it, so he must realize what to do.
I can't reach it. and pick up the pepper. And place it on the rocker so it should flip over. And the tomato should roll down. Let me see where the tomato is now. Now I can grasp it. Got it.
And here's some other applications, including auditory exploration, pose estimation, coaching, and so on, and many others. In summary, what we can get from that is that the use of modalities is relevant in neural learning for perception, given its biological background. Humans have the inherent adaptive capability of processing, for instance, in the lack of some modality, vision, for example. This functionality can be transferred to hearing or touching or something like that. And it's important that interactive robots, for them to be able to deal with those various modalities, especially if we want them to have a more human-like behavior, which might lead to a more natural human-robot interaction. Also, when applying those robots in domestic environments, when dealing with humans, the use of continual neural learning proves important due to the need for the robots to adapt in uncertain scenarios. By being capable of generalizing despite the amount of noise information in their environment, as well as by integrating the information from the available sensory modalities, we can develop robots that are more adaptable and that can be of aid in our day-to-day life. These are some of our research projects that were funded by the EU, the German funding group, by COPPE from Brazil, and so on. And this is our team. Thank you for your attention. Actually, the picture of our team is quite old because people are not being capable of coming together now because of the pandemic that's affecting all of us. And the people marked with the red circles are the ones that are still working with us nowadays. Please visit our website for more information on our work and also our YouTube channel. Thank you very much.
Excellent. Thank you very much. Let me see if I can put myself on spotlight also. All right. Let's go over some questions. I have some here. I will start with Priscilla's question from Federal University of Rio. How is the control of the different parts of the robot approached? Is there a central control, or the different parts of the robot, like the arms, have a decentralized control?
Actually, sorry about okay. The control of the robots actually sorry.
Don't be nervous.
Okay, I have not actually worked with many of those robots. Actually, this is a big problem for me because most of the work's done with the robots that work with the grasping and language understanding is from another group that works with language understanding and language visual representations. Mine is more focused on the perception part. So actually, I do not have too much of information how the Nico works in the background of it all, or if there is a decentralized control or something like that.
Okay. No problem. So let's try to one question that I have is, do you have these robots walking around the lab, or most of the problems are just in simulations?
Actually, we have some robots not walking around the lab there. We have some now robots. Okay, I was speaking about the learning was decentralized. Actually, the robots have, just answering Priscilla, actually, as I present, the robot has several different sensors that provide different kind of information. And it all depends on the kind of architecture we do. For instance, the architecture that was an end-to-end one, we had all the inputs being sent through a same, as all of them as an input to the model, and that provides the model, the robot, with a command for him to either do the grasping or to recognize something. But actually, yeah, this comes from the several sensors it has in its eyeballs, in the microphones in the ears, or the sensors in the points of the fingers and the hands. And the learning actually happens this way. Yeah, that's what I know for the most part. Regarding your question, Professor Rocha, could you please repeat it?
My question was, well, I have several here.
Okay.
I think that I will go with, in terms of what Priscilla was asking, if these solutions that you have, if they are done in a simulation, most of them, or if they are directly implemented in the robots that you have in the lab.
We implement directly in the robots in the lab, but as I mentioned, we usually use some simulation scenario first, because sometimes there can be some kind of movement that may need the robot to move its arm more than 180 degrees, and that would possibly break some kind of joint. And so we need to avoid those kind of problems, because every time there's a problem like that, there is all of a huge time load of maintenance and fixing everything. There are several euros that we have to pay for fixing it. So yeah, so actually we work a lot with the simulation environment, but then we finally implement that in the robots. But especially due to COVID, it's been very common for people to use more simulation scenarios nowadays, because not everyone's being capable of going to the campus all the time, and this brings a challenge to, I think, all of us. So.
Okay, I'm looking at another question here. Regarding your part on the perception, what do you think is the most challenging part, and how do you see this field of perception for robots like in 5 or 10 years?
What do I think is more complex in the case of perception? In the case of perception, I was dealing too much with dealing with audiovisual perception and so on. But there are some kind of social cues we use that are not that easy to get. For instance, emotional cognition brings too much problem, because it's kind of a weak label. If a person is... Oh, okay, sorry, you were frozen there. I thought that you were not hearing me.
I also
Okay.
have other questions coming, and I cannot.
Okay, no problem. Just ending. So there are some kinds of perceptions and some kind of problems that have some weak labels, like emotional cognition, in which some person may classify one person as happy, but sometimes that the same person as neutral.
But
or
for you
sad.
today, what's the most important challenge that you think for the field of perception?
Nowadays,
what do you think is like if we solve this, the industry of robots would like have a much better perception detection?
I think the audiovisual part, I think, is the most important, especially because usually when you're working with people, it's what you usually use. Or sometimes a person is far away. You need to have a good perception of the visual part. Sometimes you cannot hear the person saying something. For instance, you want to determine if someone's drowning far away, and you have a robot that possibly sometimes helps some, say if someone's drowning. You cannot hear the person calling for help, but you can see the person moving its arms in the background. So detecting pose is also, the pose estimation of the people is also pretty important in those cases, but everything is kind of visual. And
right.
It's important when dealing with people, and also for us to create some kind of human-robot, a better human-robot relation where people can interact better with robots without getting a little bit in that, okay, it's an uncanny valley. I do not feel too comfortable talking with robots. So if the robot behaves like us, is the best thing for us, for improving the relation of people with robots in this case.
Another thing that comes to my mind is normally, especially the work that you've done, it's like about perceiving the world, what's going on, and interacting with it. But normally, as you discover what's going on in terms of robotics, you also probably need a knowledge representation form, like an architecture to represent all of these things that you discovered in the world in a nice and coherent way. Does your group do some work in this regard of cognitive architectures or some form of representing knowledge discovered from the world?
Yeah, there is work on those kind of representations done by our group. Several areas, several different, when working with several different cues, as in the case of language, in the case of audio, in the case of visual parts.
If you can send some of the paper references to me later, it would be great, because we have a project here about architecture representation, and those papers could give us some very nice ideas.
Okay, I can send them to you.
Very nice. So I have another one here from Felipe. Thank you for a nice presentation. How causality is dealt with within the multisensory robotic framework? Are you aware of this part? How do you deal with causality?
Besides from what I saw from the presentation, I have not too much of a knowledge on how that is done. Actually, much of what's presented here in this presentations before I came to the group, because I arrived here during the pandemic, so actually the progress was not as intense as it was some years ago. God.
There is no problem in not knowing.
Okay, but I can provide the paper. I have the reference there. I can provide you the paper.
You presented the work of the whole group. It's natural that you don't have that knowledge of how it's implemented, because it's very detailed. Another thing, how do you see this part of perception, like the next move? I mean, when you see a robot like the ones that you mentioned here, it's like a humanoid robots to interact with humans. But how do you see this going forward for like the automobile industry, like for autonomous cars? How do you see this integrating in the future? I mean, can you envision in 10 years where we are going to be in terms of perception and interaction of the robots?
I think that given the advance in deep learning and the convolutional neural networks, I think that for autonomous cars and so on, I think that in 5 years, 10 years, it will be pretty much possible. It's important to realize what kinds of actions to take in determined situations, or not only focus on the visual part, as was shown in the example we had, but also some auditory stimuli that may be happening, because there is possibly some ambulance that's not seen, but that may be passing, and the car needs to stop before the ambulance passes. So, and possibly in the near future, also with some integration between the several different autonomous cars, this might also become more easy to manage how to interact in the traffic and so on.
And how do you see like I mean, when we think of perception, we need to have a very good recognizer, I mean, detector in the robot, right? But right. It would be very nice to have interaction with other robots around for a better detection of what's going on. Have you seen any research in these terms of connecting different robots and acting in sync?
Actually, our group does not do that, actually. But as far as I know, I do not have knowledge of any kind of work like that. Actually, not from the top off the top of my mind, but I can realize that it's pretty possible for that. What we are doing now actually is instead of using several robots for the case of perception, actually we're using we have examples with single robots in which it cannot perceive a given object on the table because there are some kind of occlusion, and it can determine that it should move in order to determine if that object is really there or not. Okay, that having several robots within sync would have this answer right away, but usually you're more interested in determining if the robot is capable of determining if it has to further investigate, further explore, or if it can determine if something is not there in a given scenario.
Okay. Final question, at least from my side.
Okay.
Do you see for perception that you have more challenges in terms of the audio part, the visual part, or other signals like sonars, lidars, and other things? I mean, in terms of algorithms to perceive the world.
I think that signal processing in general, for instance, audio, is still not that much explored. People usually explore too much on vision. They focus all their attention to convolutional neural networks and so on. And the auditory part has a much smaller contribution
in neglected, right?
Literature. So actually, I think those end up being more where it's more difficult to deal with and which should have a greater focus on.
Yeah, I agree with that. I was thinking about that when you showed the slides on the MFCC. MFCC is an algorithm that's been around for decades, and we still don't have something that's better than this, like in general.
So actually, I am working with speaker detection, and recently I came up with a more recent state-of-the-art model. I think they use a model from, I think it's Cavanelli and Banjo. It's one student from Yoshua Banjo and Yoshua Banjo that they came up with a neural network they call a SyncNet, because it uses sync functions as their convolutional functions, the convolution functions, so that they can manage to get the specific frequencies that compose an audio signal without the need for some arbitrary filter banks being predetermined. So I do not know if this will be what will move this field forward, but I think it's as an interesting concept, and that might be in the same way that previously people were doing feature engineering for visual, and then they came to feature learning. So it works in kind of similar way. Instead of you determining filter banks and then the null frequency substrate coefficients, come up with neural networks that have some kind of convolutional functions that may be able to detect specific frequencies and combine them.
All right. I don't know if this one you will answer. Priscilla is saying that by 2005, Professor Vermeter approached the way robots obeyed orders by making the robot devise a plan. Do you know how they are working on this now? This is too detailed for the parts of the robots, right?
Yeah.
Let's go for the other about the perception part. João is asking if in your work you traditionally use like common networks like ResNet, VGG, and others, or do you have specific ones trained for robots?
No, actually, I work with traditional architectures like ResNet. Specifically, my task where I worked most of the time in the group.
All right. I don't think that we have any other question by now. Hugo, thank you very much for your talk and time. Also, send my thanks to Professor Vermeter for organizing this. And I hope that the situation in Germany about COVID improves, because I'm reading that it's not that good right now. And if you need anything here from us, just get in touch.
Okay, thank you very much.
Thank you. Bye-bye. Everybody, thank you very much for joining. And I remind you that this talk will be available on YouTube later. Thank you. Bye-bye.